De-icing is defined as removal of snow, ice or frost from a surface. Anti-icing is understood to be the application of chemicals that not only de-ice, but also remain on a surface and continue to delay the reformation of ice for a certain period of time, or prevent adhesion of ice to make mechanical removal easier. Approaches. De-icing can be accomplished by mechanical methods, through the application of heat, by use of dry or liquid chemicals designed to lower the freezing point of water, or by a combination of these different techniques. Anti-icing of aircraft is accomplished by applying a protective layer, using a viscous fluid called anti-ice fluid, over a surface to absorb the contaminate. All anti-ice fluids offer only limited protection, dependent upon frozen contaminant type and prevailing weather conditions. A fluid has failed when it no longer can absorb the contaminant and it essentially becomes a contaminant itself. Even water can be a contaminant in this sense, as it dilutes the anti-icing agent until it is no longer effective. De-icing of roads has traditionally been done with salt, spread by snowplows or dump trucks designed to spread it, often mixed with sand and gravel, on slick roads. Sodium chloride is normally used, as it is inexpensive and readily available in large quantities. However, since salt water still freezes at -18 degrees Celsius, it is of no help when the temperature falls below this point. It also has a strong tendency to cause corrosion, rusting the steel used in most vehicles and the rebar in concrete bridges. Depending on the concentration, it can be toxic to some plants and animals, and some urban areas have moved away from it as a result. More recent snow melters use other salts, such as calcium chloride and magnesium chloride, which not only depress the freezing point of water to a much lower temperature, but also produce an exothermic reaction. They are somewhat safer for sidewalks, but excess should still be removed. More recently, organic compounds have been developed that reduce the environmental issues connected with salts and have longer residual effects when spread on roadways, usually in conjunction with salt brines or solids. Additionally, mixing common rock salt with some of the organic compounds and magnesium chloride results in spreadable materials that are both effective to much colder temperatures as well as at lower overall rates of spreading per unit area. Direct infrared heating has also been proposed for de-icing purpose. This heat transfer mechanism is substantially faster than conventional heat transfer modes used by conventional de-icing due to the cooling effect of the air on the de-icing fluid spray. Solar road systems have been used to maintain the surface of roads above the freezing point of water. An array of pipes embedded in the road surface is used to collect solar energy in summer, transfer the heat to thermal banks and return the heat to the road in winter to maintain the surface above 0 degrees Celsius. This automated form of renewable energy collection, storage and delivery avoids the environmental issues of using chemical contaminants. It has been suggested recently that superhydrophobic surfaces capable to repel water can also be used to prevent ice accumulation leading to the isophobicity. However, not every superhydrophobic surface is icephobic and the method is still under development. In particular, the ice-frost formation over the entire superhydrophobic surface is inevitable as a result of undesired interdroplet freezing wave propagation, initiated by the sample edges. Moreover, the frost formation directly results in an increased frost adhesion, posing severe challenges for the subsequent defrosting process. By creating hierarchical surface, the interdroplet freezing wave propagation can be suppressed whereas the ice-frost removal can be promoted. The enhanced performances are mainly owing to the activation of the microscale edge effect in the hierarchical surface, which increases the energy barrier for ice bridging as well as engendering the liquid lubrication during the de-icing, defrosting process. Chemical or chemical de-icers share a common working mechanism. They chemically prevent water molecules from binding above a certain temperature that depends on the concentration. This temperature is below 0 degrees Celsius, the freezing point of pure water. Sometimes, there is an exothermic dissolution reaction that allows for an even stronger melting power. The following lists contains the most commonly used de-icing chemicals and the typical chemical formula. Inorganic salts: sodium chloride, magnesium chloride, calcium chloride, potassium chloride. Organic compounds: calcium magnesium acetate 6, potassium acetate, potassium formate, sodium formate, calcium formate 2, urea 2, a common fertilizer. Agricultural byproducts: alcohols, diols and polyols, methanol, ethylene glycol, propylene glycol, glycerol. Fluid types: there are several types of de-icing fluid, falling into two basic categories. 1. De-icing fluids: heated glycol diluted with water for de-icing and snow, frost removal, also referred to as Newtonian fluids. And 2. Anti-icing fluid: unheated, undiluted propylene glycol-based fluid that has been thickened, also referred to as non-Newtonian fluids. Applied to retard the future development of ice or to prevent falling snow or sleet from accumulating. Anti-icing fluids provide holdover protection against the formation of ice while the aircraft is stationary on the ground, but when subjected to shearing force such as the airflow over the fluid's surface, an aircraft accelerating for takeoff, the fluid's whole rheology changes and it becomes significantly thinner, running off to leave a clean and smooth aerodynamic surface to the wing. In some cases both types of fluid are applied, first the heated glycol-water mixture to remove contaminants, followed by the unheated thickened fluid to keep ice from reforming before the aircraft takes off. This is called a two-step procedure. Methanol de-ice fluid has been employed for years to de-ice small wing and tail surfaces of small to medium-sized general aviation aircraft and is usually applied with a small handheld sprayer. Methanol can only remove frost and light ground ice prior to flight. Monoethylene, diethylene and propylene glycol are non-flammable petroleum products, and similar products are most commonly found in automotive cooling systems. Glycol has very good de-icing properties and the aviation grade is referred to as SAE, ISO, AEA Type 1. It is usually applied to contaminated surfaces diluted with water at 95 degrees Fahrenheit using a cherry picker on a truck containing 1,500 to 2,000 US gal for on-ramp or departure runway entry point application. Color-dyed fluid is preferred as it can be confirmed easily by visual observation that an aircraft has received a de-ice. Runoff Type 1 appears to turn slush a pink tinge, hence the term pink snow. Otherwise, all Type 1 fluids are orange. In 1992, the Dead Sea Works began marketing a de-icer based on salts and minerals from the Dead Sea. Pneumatic systems. In-flight ice buildups are most frequent on the leading edges of the wings, tail, and engines. Lower-speed aircraft frequently use pneumatic de-icing boots on the leading edges of wings and tail for in-flight de-icing. The rubber coverings are periodically inflated, causing ice to crack and flake off. Once the system is activated by the pilot, the inflation-deflation cycle is automatically controlled. In the past, it was thought such systems can be defeated if they are inflated prematurely, if the pilot did not allow a fairly thick layer of ice to form before inflating the boots. The boots would merely create a gap between the leading edge and the formed ice. Recent research shows bridging does not occur with modern boots. Electric systems. Some aircraft may also use electrically heated resistive elements embedded in a rubber sheet cemented to the leading edges of wings and tail surfaces, propeller leading edges, and helicopter rotor blade leading edges. This de-icing system was developed by United States Rubber Company in 1943. Such systems usually operate continuously. When ice is detected, they first function as de-icing systems, then as anti-icing systems for continued flight in icing conditions. Some aircraft use chemical de-icing systems which pump antifreeze such as alcohol or propylene glycol through small holes in the wing surfaces and at the roots of propeller blades, melting the ice, and making the surface inhospitable to ice formation. A fourth system, developed by NASA, detects ice on the surface by sensing a change in resonance frequency. Once an electronic control module has determined that ice has formed, a large current spike is pumped into the transducers to generate a sharp mechanical shock, cracking the ice layer and causing it to be peeled off by the slipstream. Air bleed systems. Many modern civil fixed-wing transport aircraft use anti-ice systems on the leading edge of wings, engine inlets and air data probes using warm air. This is bled from engines and is ducted into a cavity beneath the surface to be anti-iced. The warm air heats the surface up to a few degrees above 0 degrees Celsius, preventing ice from forming. The system may operate autonomously, switching on and off as the aircraft enters and leaves icing conditions. Environmental impact. De-icing salts such as sodium chloride or calcium chloride leach into the soils, where the ions may accumulate and eventually become toxic to the organisms and plants growing in these soils. The chemicals could also reach water bodies in concentrations that are toxic to the ecosystems. Organic compounds are biodegraded and may cause oxygen depletion issues. Small creeks and ponds with long turnover time are especially vulnerable. Propylene glycol used to de-ice aircraft can contaminate drinking water supplies and harm aquatic life. Some airports are now capturing and treating de-icing runoff before allowing it to enter waterways. Applications. Aircraft on the ground. When there are freezing conditions and precipitation, de-icing an aircraft is crucial. Frozen contaminants cause critical control surfaces to be rough and uneven, disrupting smooth airflow and greatly degrading the ability of the wing to generate lift, and increasing drag. This situation can cause a crash. If large pieces of ice separate where the aircraft is in motion, they can be ingested in engines or hit propellers and cause catastrophic failure. Frozen contaminants can jam control surfaces, preventing them from moving properly. Because of this potentially severe consequence, de-icing is performed at airports where temperatures are likely to be around 0 degrees Celsius. In flight, droplets of supercooled water often exist in stratiform and cumulus clouds. They form into ice when they are struck by the wings of passing airplanes and abruptly crystallize. This disrupts airflow over the wing, reducing lift, so aircraft that are expected to fly in such conditions are equipped with a de-icing system. De-icing techniques are also employed to ensure that engine inlets and various sensors on the outside of the aircraft are clear of ice or snow. De-icing on the ground is usually done by spraying aircraft with a de-icing fluid based on propylene glycol, similar to ethylene glycol antifreeze used in some automobile engine coolants. Ethylene glycol is still in use for aircraft de-icing in some parts of the world because it has a lower operational use temperature than propylene glycol, but PG is more common because it is classified as non-toxic, unlike ethylene glycol. Nevertheless, it still must be used with a containment system to capture the used liquid, so that it cannot seep into the ground and water courses. Even though classified as non-toxic, it has negative effects in nature, since it uses oxygen during breakdown, causing aquatic life to suffocate. In one case, a significant snow in Atlanta in early January 2002 caused an overflow of such a system, briefly contaminating the Flint River downstream of the Atlanta airport. Many airports recycle used de-icing fluid, separating water and solid contaminants, enabling reuse of the fluid in other applications.